welcome to all of you to the public talk today as a part of our year-long celebration of Azadi Ka Amrit Mahotsav. Today, Professor Venkatesh Raman will be giving a talk. So, before he starts, let me say a few words about him. So, he did his PhD from University of Waterloo, and before that, he did his master's from IIT Kanpur. And then after that, after some small stay abroad, he has been in IMSc from 90 to 93 onwards. And so I have known Venkatesh from August 2000. Yeah, so that is the time when I did my undergraduate course in algorithms, and from that time I have known him. So that time Venkatesh did his PhD in very classical object of sorting in implicit data structures. But during this period of time, he picked up other things like parameterized algorithms. And luckily for me, when I was started to interact with him, I did not get the share of data structures, which he's going to speak about. I got the other share, other piece, that was parameterized algorithms. So yeah, so I actually, more or less, I thought that I will be doing data structures, and that is one of the reasons why we approached him. But like in my first meeting as an intern, I was given a problem in parameterized algorithms, and that is what I started to do, and I'm still doing it, and probably I will keep doing it for foreseeable future. So Venkatesh expertise is both in data structures and parameterized algorithms. So his earlier work was in succinct representation, and he has a very highly acknowledged papers in this area, and so today Venkatesh decided to talk about succinct representation. And what succinct representation means, like, is basically you have something and you will have to represent it with as few bits as possible, and you have to prove some lower bounds and upper bounds. So yes, it's our great pleasure that Venkatesh agreed to give a talk to all of us. So with these words, I request Professor Venkatesh to come and deliver his talk. Thank you.
Thank you for the introduction, and thanks Rijit for persisting with me. So that's the title of my talk, and hopefully I will have some time to talk about this towards the end of the talk, because most of my talk is going to be about this area of succinct or space-efficient data structures. I will not say much about that. Hopefully I will say a little bit about it at the end, but the bulk of the talk is going to be motivating the questions that led to the birth of this area, okay, and sort of history of how it all began. And this is not about representation theory, so I should tell you about. Maybe there is, I don't know. Okay. Okay, so the starting point of the talk, the story is about this fundamental pattern matching or string matching problem, where you are given a text which is a sequence of characters of a large length from some finite alphabet, and another text which is a pattern, and we want to know whether P occurs in T as a contiguous set of positions. Find the number of occurrences of P, find all occurrences, the positions where P occurs in the text if it appears. And there are more sophisticated questions in real world about, sometimes you allow mismatches of the pattern with the text, a few mismatches. Sometimes, okay, so, this is such a fundamental problem. I'm sure many of you will be, do a Control F and you're searching for some pattern in some text, or you will be doing this in an editor. And it has also far-reaching applications in search engines like Google, because Google question is essentially that, right? If you think of the concatenation of all the websites as one big string, then your query is essentially some pattern, and you're trying to find it in that big text. And so here's an example where okay, so it did not have a good enough figure. I should have pushed this all the way up to AB. So there are two overlapping occurrences of this pattern in this text, and so our problem is to design an algorithm to figure this out. Okay. So a naive algorithm, for example, would be is to take your pattern and slide it on the text, looking for matches. So you know keep comparing your pattern character with the text character, and until you find a mismatch. Once you find a mismatch, you sort of slide the text by one character and start looking for matches again until if you find a match. Also, since you have to find all occurrences, you still have to keep going. And so this is a very naive algorithm which you can easily verify that it takes, if m is, okay, I think I said it in the first slide, m is the length of the pattern and n is the length of the text. So this algorithm, you can verify that it actually, in the worst case, can take m times n comparisons, character comparisons. But there are more efficient algorithms. There's an algorithm, popular algorithm due to Knuth, Morris, and Pratt, which we teach it in our undergraduate algorithms course, which essentially says you take your pattern, pre-process it somehow, and find what is called some successor function. So whenever there is a mismatch, instead of sliding by one character, you've learned something about the matches. So you know that this is B, this is C, this is N. So why compare this A with B? So you can sort of slide faster and do it more efficiently. And this algorithm has a running time m plus n rather than m times n. So this is very well solved. This is as good as you can get, because you have to look at the text, you have to look at the pattern, and that's essentially what it's doing. And there are after this algorithm was discovered, there have been a number of other approaches. Some work much better in practice, and others are linear time in the worst case, different approaches. Okay, so are we done? Well, actually, if you think about your real problem, even n is too much time for us, because for every query you cannot be spending time proportional to the length of the text, which is very large. So imagine your Google query or something. You have a query and you don't want to be able to spend time proportional to the length of this entire set of pages, right? That's too much. A simple analogy would be like, if you want to look for a word in a dictionary, okay? Some of you, I have looked for a word in a physical dictionary, no longer now, but you don't go and search one word at a time. Depending on if it's a word starting at X, you will go towards the end, and with about 2-3 pages search you will find it. And similarly, if it is starting with B, then so, and the reason you are able to quickly find it because the dictionary is organized lexicographically. Right? Just imagine if it is not organized lexicographically, right? So the question here we are asking is, take this text, pre-process it somehow, this long text, which could be a huge genome sequence, or it could be a set of pages, websites, organize it nicely, come up with some sort of a structure so that your queries take time proportional to the length of the query, not proportional to the length of the text. Okay, so that is our real problem, which is that pre-process the text so that you can query for your pattern in time proportional to the length of the pattern, because we are running tens of thousands of queries every day. It's not you can't be spending time proportional to the length of the text. And this was very well studied by a very elegant data structure called suffix trees. This was discovered in 1973, and much of my talk is going to be about trace the history of this data structure, what it is, and what were some enhancement done to to make it practical. Okay, so feel free to stop me at any time if there are any questions. So before I talk about suffix trees, I should tell you what is a prefix and suffix of a text. So a text, remember, by the way, text is also called a string or a pattern, and given a string, a prefix is the first few characters. Okay, so you start at position x1 and go up to some position, and that string is called prefix, and suffix is the last few characters. Okay, so on this example, this is a prefix of this text and this is a suffix, and prefix, you go up to any length and that would be a prefix. So there are n, if the text length is n, there are n prefixes and n suffixes, right? Because you have so many different options for the starting point or the end point. So here is the big simple observation which led to this development of suffix trees is that your pattern occurs in the text at position I if the pattern is prefix of the suffix of t starting at position I. Okay, it looks very mouthful, but it's very simple observation. It simply says that your pattern p occurs in the text, let's say at starting position I, then you look at the suffix starting at I, right, which starts at I and goes all the way to the end, and your p is a prefix of that suffix. Okay, so Weiner's idea was that let's collect all the suffixes in the text, there are only n of them, put them into a tree, and whenever I have a pattern matching query, I just check whether it is a prefix of any of the suffixes. Okay, questions? Yeah, so that led to this, what is suffix tree. So here is an example of a suffix tree for this text. Remember, at this point we only have the text, right, because we are pre-processing the text. So take the text, let's say banana. For some technical reason I'm going to add an n marker. I will explain why I do that in the next slide. Then I write down all the suffixes. Remember, suffixes are all substrings ending at the end. So it's $, $, $NA, $ANA, and put them all in a tree of this form. And what is this tree of this form? If you read, you all know what a tree is, right? In computer science, a root is always at the top of the tree, leaves are at the bottom, and if you read up, look at the path from a root to a leaf, that would correspond, and concatenate all the characters on the edges, that would correspond to a suffix. Okay, so this $ANA corresponds to a suffix, and this leaf is labeled with number 2 to say that suffix starting at position 2. Right, this suffix is captured by this path, and $A is the suffix starting at position 6, so that suffix. So every suffix is represented here. So every leaf has a number, every edge has a character, and if you read the path from a root to a leaf, that corresponds to a suffix. Okay, so that is a suffix tree. Simple enough. Now you can imagine how you would search for a string in the suffix tree, right? Okay, here's a formal definition quickly. It's a rooted tree, it's an ordered tree. There is an order among the children. Every leaf is labeled with a suffix, which is the starting position of the suffix. Every root to leaf path concatenation of the edge labels corresponds to the suffix labeled at the leaf. No two edges of a node have the same character label. This is very important, right? When you basically we are sharing the edges. One little caveat, we want all suffixes to end in a leaf, and which means that you don't want one suffix to be a prefix of another suffix. So if AB is a suffix and AB is a suffix, AB will end in an internal node because you have to extend it to another AB. So we don't want this, and that's why we add this special symbol $ at the end, a character which does not come in the string at all. So that ensures that every suffix ends in a leaf. How do you search for your pattern now, given this suffix tree? Well, you want to search for ANA, then you follow from root, look for an edge with an A, look for an edge with N, look for an edge with A, and then you say, yes, ANA exists, success, and the time I spend is proportional only to the length of the pattern, because I've just followed through this pattern. And extra bonus is that if you follow through all the way and go to the leaves of the tree where you ended, the leaves correspond to the positions, starting positions of these pattern. Okay, remember that was one of the problems, and you get that also here.
Okay.
Yeah.
You have binary sequence.
Yeah. Simpler because there will be only 2 children, right? Or yeah. Binary, when you say, you mean there are only 2 characters. Yeah, it will be much simpler. So in fact, I did not say, for the most part of this talk, you can assume that the alphabet size is a small constant. Okay, it could be 2, could be 4. For biology applications, it is ATGC. There are only 4 characters. In fact, much of suffix trees were developed for biology, computational biology application. So you won't lose any generality by assuming that the alphabet size is 4. Okay, it's easy to fix it in your mind. And if you want to search for, let's say, bank in this suffix tree, I look for an edge with character B, an edge with character A, edge with N, and there was no edge with character K coming out of this node, so I end the search here and report that the pattern does not exist. Okay, good. So that's more or less the end of the story. We have this nice tree which collects all the suffixes. Now we can search in time proportional to the length of the pattern. Okay, well, okay, so I already said it takes only time proportional to the length of it. So this is important, right? Regardless of the size of the text, I am not looking at much of the text at all. I just follow through this pattern in this tree and I stop and I found it, or I don't. You want to know the number of occurrences? That is exactly, again, it's a very simple observation. It's just the number of leaves in the subtree where your search ended. Okay, so on this example, your search ended here. The number of occurrences of this pattern ANA is 2 because the number of leaves in this subtree is 4 and 2. Okay, now how do you find that? I'll come to that later, because at this point I'd spent time proportional to the length of the pattern and stopped at this node, and if I proceed and go and find the leaf, that's going to take me more time. Okay, I'll come to that later. But one of the things is the whole thing is static, so we could pre-compute this number and store at every node. Okay, that's one easy fix. You want to find position of all occurrences. Again, the leaves labels tell you all the positions, so you should be able to pre-compute and store them as one way out for this. And construction time, well, that was the big contribution of Weiner in 1973. More than developing this data structure, which is very simple. I mean, in hindsight, it is simple, but at that time, it was somewhat non-trivial, I would say. But how much time does it take to construct this suffix tree? Anybody wants to guess? So there are n suffixes and you want to put it in this tree. Okay, and these suffix lengths are n minus 1, n minus 2 up to 1. So you can just sort of keep inserting all the suffixes into the tree. So insert one suffix and then take the next suffix, insert it there. Only thing you need to do is to share the edges, right? If you have 2 suffixes starting at A, don't create a new node, just share that edge and branch. So naively, this will take how much time? N square time, right? Yeah. So what Weiner actually did, and many more people after that, is they gave a linear time algorithm to construct these suffixes, because these are not just some arbitrary set of n strings, because they are related, so you could take advantage of that and construct it in linear time. But now you should complain. A suffix tree actually can have n square nodes. The way I have drawn the suffix tree, I mean, if you, for example, if you take your text as A, B, C, D, E, and then no edge will be shared. A, B, C, D, E will be suffix, B, C, D, E will be a suffix, C, D, E will be a suffix, and the total number of nodes in the suffix tree will be n square. So how are they able to construct it in linear time? Well, they didn't construct this suffix tree. Some compressed version of it, and the compressed version is simply what is contributing to this long paths is a lot of nodes with one child. Okay, so compress them all into one big edge, concatenate all the labels and put it like this, then you don't have a node with exactly one child. Okay, then this is an easy exercise, first year graph theory course. If you have a tree where every non-leaf node has at least 2 children, then the number of nodes is actually linear because it's bounded by the number of leaves, and we know that the number of leaves is linear. Okay. However, this edge labels can still take, okay, maybe I'll use n square space, right? Because we have this edge label which could be very large, and there are a lot of edges which could have a lot of long edge labels. So the space to store the edge labels could be n square, even though the number of nodes is linear. Well, we'll deal with that. But now here is one more thing, that if I want to output all occurrences, once my search ends at some point, I have to go and get to the leaves. You can actually go and visit the subtree because the number of nodes you will visit is proportional to the number of leaves for the same reason. So it's the output size, so you can actually visit and report all possible occurrences. But the labels can still occupy n square space. Okay. So a bulk of early developments on suffix trees is to reduce the space somehow, because so here is a simple trick to reduce the label length. Because the labels are arbitrary, and if you are used, if you just go down and implement this, having uneven labels and on the edges can be messy. One way to simplify is that these labels are actually substrings of your text. So you can replace them with start and end position of these texts, and that is just 2 numbers. Uniformly 2 numbers on every edge, so that way you have made your space to overall only linear. Okay. Now, so this was the development of suffix trees, and people were quickly realizing that suffix trees can do a lot more than doing your pattern matching. In fact, now it has reached a stage that anything you want to do with text, you cannot avoid suffix trees. So again, one of the early development of an algorithm which made Knuth to call this as the construction algorithm as the algorithm of the century or algorithm of the year, I think there are some debates going on, is suppose I want to find the longest common string of 2 long strings. Okay. So I have this 2 long strings. So we have moved away from the pattern matching problem. I'll come back to it later, but I want to say that suffix trees have a lot more other uses. So you have 2 strings and you want to find the longest common string, right? So for example, here n, a, n would be one of the common strings, and maybe it is the longest. So how do you find this? So Karp, Miller, Rosenberg in Stock 1972 gave an n log n algorithm, and Knuth conjectured that n log n is the best you can do. This conjecture was short-lived because just the next year, using Weiner's linear time construction for suffix trees, this problem was solved in linear time. And it's actually not very hard to actually do it. Maybe I won't get into it because I think it's already probably getting technical. So what you do is you construct what is called a generalized suffix tree. Take these 2 strings, put them together with a delimiter, and construct this big suffix tree for this big string. Now you can see that the longest common string is the deepest node in this tree, which has both suffixes, suffixes from both the strings in the leaves. Okay, and this is something you can, after you construct the suffix tree in linear post-order traversal of the tree, you can do it. Okay, so moving on, about 10 years later, Alberto Apostolico, who is one of the active string theorist, okay, I mean, who works in string matching, wrote this paper which said, myriad virtues of subword trees, and the suffix trees had various different names. This is a book, Algorithms on Strings, Trees and Sequences, Computer Science and Computational Biology by Dan Gusfield. Dan Gusfield was actually here. He gave a talk in meeting Rahul organized about 5 years ago. Something.
I think he was getting a joint invitation.
Right. Here there was a computer science conference, and then we also used it to. So if you look at the contents of his book, this is a table of contents, and if you see, suffix trees and their users, introduction, linear term construction, first application of suffix trees, it goes on about 17, 18 applications, and the next page, more applications of suffix trees, and goes on. So that tells you that, quickly it became so powerful that any problem, algorithmic question using text, finding mismatches, repetitive strings, all kinds of longest common strings, you cannot avoid using suffix trees. There is this conference, Combinatorial Pattern Matching. It's an annual conference. In 2013, they had a special session on 40th anniversary of the suffix tree.
So who owns that?
Weiner.
This concept,
Hmm?
when was the notion of suffix tree? Before this.
73. That's why this says it's 40th anniversary. In this person, Weiner, who discovered this tree and used it for pattern matching. I mean,
Very counterintuitive. Not obviously doing that.
okay.
I understand slightly.
Uh-huh.
Suffix tree feature.
Now, despite all these powerful applications of suffix trees, they were not used much in practice in large-scale applications until late 90s. Okay, so you saw this book. The book was 87, which had about 20 applications of suffix trees. But when it comes to these huge biology applications or search engines, they were not really used in production that much. Why do you think? Time for construction, okay, time for construction, it was linear time. And also, construction happens very rarely. Right? It's like the dictionary example I say. Once a year you build a dictionary, and it's okay if it takes more time. The query time is what you want it to be fast. So similarly here, it was nice that they constructed in linear time, but in my opinion, for the pattern matching question, that was not very important. There are other applications where it was important, like the longest common substring. But space was the big nuisance. Okay, let's do a quick calculation of accounting of space usage of suffix trees, nitty-gritty. So if your text, if you are trying to represent, take the text which takes n characters, alphabet size is sigma, so to represent the text it takes n log sigma bits, right? Because if your character is like 4, then you need 2 bits, 0, 0, 0, 1, 1, 0, 1, 1 to represent these 4 objects. So n times 2, n times log sigma is the number of bits you need to represent just the text. Now if you go back and look at the tree representation, the whole suffixes and the leaves and all that, and do a careful calculation, the leaf labels takes you n log n bits, which is because it's a permutation, there are n numbers on the leaves. But the tree itself takes, there are 2n nodes, and there are so about 2n edges, and each edge is what? A pointer. A pointer is an address to one of those nodes. So if there are n nodes, then an address to one of those nodes will take log n bits, because it's one of the n numbers, or 2n numbers. And then on the edges you are representing some starting and end point of some substring, that will sum 2 numbers. So it takes about 7 n log n bits for the suffix tree whereas the text is only n log sigma bits. So if you take sigma to be 4 and n is, let's say, 1,000,000 characters you want to represent, log n is 20, I've made all kinds of approximations here, then the suffix trees take about 70 times the text. Okay, basically 7n log n. If you put log n equal to 20, we are talking about 140n, whereas n log sigma is only 2n. So 2n and 140n. So suffix trees take about 70 times the text, and this was clear no-no for large scale applications, particularly in genome sequences. Okay. So there were more savings done. Maybe I'll quickly go over them. On the edges you are representing two numbers. There are ways to get rid of it, remove two numbers and keep only one number. Just keep only the length of the substring, not necessarily the starting and ending point. Then when you search, you just sort of skip that many characters. You don't necessarily do your comparisons, and you get to a leaf and you'll do some confirmation one more time. Okay. So that reduces about 1 n log n. And then more ideas came in that we actually can even skip the lengths. This is actually where one of my PhD students, Srinivas Rao, at that time, this was in that paper, 95 or something, where we said you don't even need to remember the length. Somehow we can figure that out doing some longest common prefix kind of computation. So finally what is left is the permutation of the leaves and the tree. Okay, so somehow that's all. So we've done a lot of reduction. Now the tree itself, as I discussed in the previous slide, it takes about 4n log n. 2n nodes, pointers, that's about 2n log n bits. And can we do better than that? This is the question. So this is where this whole area of how much space do I need to store an n node tree came up, okay? Because that seems to be the big bottleneck. Now, so this a person named Guy Jacobson wrote a paper who said, oh, you don't need order n log n bits, order n bits are enough. And this was his PhD thesis. He was from Carnegie Mellon, and then he went to Bell Labs. And then Ian Munro and his team at Waterloo picked it up, and they did a lot of optimization, and this thus was born this area of succinct ways of representing objects, trees, anything for that matter. Now I'll tell you what that means. So again, something about Ian, I should tell you, that in 70s and 60s and 70s, when formal analysis of algorithms was taking place, Knuth and Tarjan, people were talking about linear time algorithms, improving from n cubed to n squared to n log n, NP completeness, everything was about time. Okay. Very few groups, particularly some complexity theorists, and very few groups were looking at space as an important resource. And quickly it was not very fashionable to look at space because memory was becoming very cheap, right? So it's no longer fashionable to look at space as a resource on the algorithms. But Ian kept at it. He asked a lot of theoretical questions in the context of data structures, implicit data structures, space efficient algorithm to find the median of n numbers. Many of these things came from his group. And so when, in 90s, suddenly space became important, not because space was becoming more expensive, but data was exploding, right? And people wanted information in handheld devices and so on. So suddenly when space was becoming important, here is, we have seen a lot of examples where theory staying way ahead, waiting for some practical things to happen to utilize, right? So this is one such example where he was working a lot on space efficient structures, and the group was geared to deal with how do we succinctly represent a binary tree. Now before we talk about it, let's do some math, right? How many number of trees on n nodes, number of distinct ordered trees on n nodes is the famous Catalan number, which we teach in the discrete math course, which is 2n choose n by n plus 1, which is roughly 4 power n by this number. So now if you want to distinguish two trees on n nodes, then log of this many bits is required. It's like, if you want to represent a number between 1 and 1000, you need log of 1000 bits to represent any number. So in that, similarly, so if I want to represent a tree on n nodes, ordered tree on n nodes, then log of this number is the number of bits represented to distinguish one tree from the other tree. And that log of this number is actually only 2n bits. Okay, because it's log of 4 power n. So the question was, can you actually represent a tree on n nodes without using all those pointers which we normally use in computer science, which takes n times log n bits, to something like 2n bits, because this has an immediate implication for space saving in suffix trees, right? Of course you can, because if you want to represent an object from 1 to 1000, there are 1000 trees and you want to represent in log of 1000, you say, okay, I am tree number 57. So think of some canonical ordering of the elements in the set and just give the number to that tree, right? So you say I'm tree number 57, you just have to remember only 57, write that down. That takes only that many bits. But it's completely useless for our application, because I need to know I am at this node, what is my left child, what is the right child, what is the parent, just saying this I am tree number 57 doesn't help. Okay, so the point is, you want a 2n bit representation, 2n ideally something like this, where you are also able to perform the standard navigation which we do on trees efficiently. Okay, now, why I say this is a general area is, but you can ask this question for any collection of objects. You have a collection of objects, you have a collection of graphs on n vertices, then you can ask, okay, how much space do I really need, and be able to perform what I would normally do on a graph in reasonable time, in whatever time I would do in this explicit representation. Okay, and yes, so people came up with a 2n bit representation like this. So here is a tree on n nodes. Okay, do a depth first search of this tree, and every time you visit the first time, you do an open bracket, or you can put a 0 and close bracket can be 1. So I start from 1 and that's open bracket, and then I visit 2, it's an open bracket, 3, I visit 4, open bracket, and 4 is done, so I will close it, and then I come back, 3 is done, so I close it, and then I come to 5, 2 is done, close it, and so on and so forth. So every node gets like an open bracket and a closing bracket, so 2 bits per node, so that's like a 2n bit representation. Okay, now you can associate with every node one of the open brackets. Now all your navigation questions on the tree now boils down to something on this parenthesis sequence. You ask, okay, for example, the left child of a node would correspond to the next parenthesis, right? Left child of 1 would be the next open bracket. That's 2. Left child of 4 would correspond to the next open bracket. Well, there is no open bracket, so there is no child of 4. Okay, so you can basically translate everything what you want to do in this small succinct representation and ask questions on this data type. Okay, but the question is, yeah, so exactly what these operations are, they're a lot more subtle. Yes, you need to come up with a whole lot of operations on this bracket sequence. And the second thing is, how do you find them, right? Because it's just only 2n bits. How do I can't spend linear time to find this. I'm trying to find it in constant time, because in this tree, if I want to know the third child, I just go there in constant time. So I can't compromise on time as well. Okay. So at this point, I should say what is time. Okay. So I've been very sloppy about this. So the whole thing works in this model of log n bit architecture. So think of your whole computer is split into words of size log n. Okay, so we're talking about 64-bit architecture now, so you can think of n as at most 2 power 64, which is reasonable. And any computation you do on this blocks of size log n, the word of size log n, we assume is doable in constant time. Okay, so in this model, we want to support all the queries on this parenthesis sequence in constant time. And that's what Monroe and his co-authors did. They showed that an ordered tree on n nodes can be represented using 2n plus some little o of n bits, which means asymptotically something smaller than n. It'll be like n by log n or n log n by log n. And support the standard operations like given a node, its parent, ith child, subtree size, a lot of these things can be supported in constant time, where time is what I said in this previous slide, that with some constant number of operations on some log n bit words. Very soon, I know it opened a lot of papers. Many people came up with different kinds of representation, different, not just parenthesis sequence, some 0-1 sequence, visit the tree in some other order rather than depth first order, and that helped in finding some other kind of operations faster. And it made the space for suffix trees order n bits for space for the permutation, because the tree has now space is reduced. And and then this work went on and on. There are a lot of people developed even further space reductions, probably at the cost of a little bit more time and so on. I talked about this Burrows-Wheeler transform in the meeting Rahul organized. It is a transform of the given text. So you take your text, do some cyclic shift, take the last characters, order them, something you don't need to know, but it just takes the text T, transforms it to another text T, which has certain nice compression properties, which means that certain same set of characters appear together. So instead of saying A 100 times, you can say A and 100. Okay, so that reduces the space further, and the developments in succinct data structures resulted in an index called FM index for the name Ferragina and Manzoni, which made pattern matching in this transform possible in pretty good time. And it was implemented in this bowtie genomic sequence analysis package. In fact, this is an actual text from bowtie software. Okay, I can't understand what this says, but maybe the biologists can. It says an ultra fast, memory efficient short read aligner, and it indexes the genome with a Burrows-Wheeler index to keep its memory footprint small. Okay, so that's sort of the story of a data structure which came out of a natural practical problem, went through a lot of enhancements, and this theoretical developments on space efficient thing nicely fit into this to make this space much better and implementable in a production package like bowtie. Okay, so I'm going to spend the next 5-10 minutes a little bit giving you tools of the trade, right? For yeah, yes, yeah. Mm-hmm.
Suppose we have a dictionary.
Yeah.
Suppose we have a dictionary.
Mm-hmm.
Is it too simple an example to build a suffix tree for a dictionary, or?
See, suffix tree is for any long text, one text. So take a text, large text. So you can
I take a dictionary.
For example, you can concatenate all the words in the dictionary and you can build a suffix tree for it.
So will it have a special structure? Because we know dictionary is organized in a particular way.
Right.
Or is it a succinct representation of, can you make the dictionary simpler?
He's asking if you already know there is a structure, like in dictionary there is some ordering already there. Can you use that in the data structure?
See, the thing is, the suffix tree is used to search for substrings. It is used to search for substrings of your given text. So the structure really doesn't matter, because you're looking for all possible substring, subwords in your text and see what. No, the reason I said is about pre-processing and building something helps you for search. I gave that in that analogy, that because you're going to do a lot of queries, it makes sense to take your text and build something out of it so that searching is faster. So in that sense, we are taking the text and building this tree where, the queries are slightly different here and there. That's the way I would. Succinct part comes later. So you build a tree, and then we are trying to do various ways to reduce the space. So that's this later part of it.
Depending on the length of the query, can one construct only a partial suffix tree?
So the thing is, query you don't know in advance.
If it is like bound by some length.
Okay, so if you're saying, suppose I tell you my query lengths are going to be bounded by something. Yeah, so then you don't, because then you are not searching for any substring, so you should be able to build a version of suffix tree where the substrings you are searching are bounded. Yeah.
So that would that save space like enormously, or would it?
I have to think about it. That seems like an artificial. Sorry.
Alignment thing like what Votai does. The text is 3 billion base pairs, but the pattern might be 100 or 200 base pairs. So you won't have a pattern of 1,000 or 10,000 base pairs. That
Okay, so then maybe you don't do suffix trees, you do something else. There are other ways of you taking advantage of this. Yeah. I don't think suffix trees alone. Suffix trees seem like a very generic thing to search for every substring. If you say your pattern lengths are bounded, there are maybe other ways of taking advantage of that. Okay, just to give you a flavor of the tools of the trade, this is one of the fundamental tool here. Okay, so it's a very simple representation problem. You have an n-bit string. Okay, so n, just a Boolean 0-1 bit vector, and the two queries I want to support are, I give you a position and I want to say, okay, how many ones are there to the left of it. Okay, so it's a string of length 200, and I say how many, some 0-1 string, and I ask how many ones are there to the left of the 70th position. And the second query is, give me the position of the 40th one. Okay, now these are the queries which are used in this parenthesis sequence and all the succinct representations, because typically when you convert the navigation operation on the parenthesis, you look like, okay, I am at position 5, my child would be somebody who's at position 7 and 14 or something like that. So you need to answer these questions. Okay, now at the first look of it, you will say, what's the big deal about these questions, right? Okay, that's an example. Yeah, give me a position, I want to know how many ones are there, I will do a search and count, right? But that's like linear time. I want to do this in constant time. Given a position, I want to know how many ones are there to the left of it in constant time. That means you're allowed to look at some 3-4 entries and we should be able to answer that. You can't just go and say, I'm going to scan all the way and tell you that's going to be linear time, and that's just prohibitive. Alternatively, you can actually answer in constant time with additional order n log n bits, because the whole thing is static. Okay, I'm not changing the string. So you can pre-process, compute all the answers and store them in a table, right? For every position you store how many ones are there to the left. You have a huge table, then query comes, you look at the answer and get it, okay? But that takes too much space. That's not allowed for me, okay? So what we actually can do it is, can support in constant time using additional little of n bits, something asymptotically smaller than n additional bits. And the high level idea is to store some sparse answers for some sparse positions, not for every position. And then if you hit a query somewhere in between, you need to do some work. to do that. And you can compress even better. Suppose I tell you that the bit string has only m ones, okay? Then the information theory lower bound changes, because number of strings, n-bit strings with m ones is n choose m, right? So the information theory lower bound will be log of n choose m, and you can actually store such a string, I don't know whether it is, yeah, with essentially this much space plus some lower order term, and you can support the queries in constant time. And these, I run out of time, but these tend to be the tools of the trade, which used in succinct data structures quite often. And the first term is information theoretically optimal space, and can be much smaller than n, sometimes can be much smaller than m log n, because that's an alternative way of storing this. Okay, so to conclude, I want to say that succinct data structures is a topic which is reasonably matured now to be a sub area in data structures. It grew out of, and it has a lot of applications, as I told you about, in large search engines and biological applications. And people have actually gone and implemented and created packages for succinct data structures, one in Australia, one in Italy, one in Chile, and so on. The real challenge is that most of the work is on static data structure. You're given a static tree, given a static n-bit string, you do all kinds of pre-processing, and the trade-off is between time and space. How much space? Because if you store all the answers, you can quickly answer your query. But if you store a partial set of answers, you reduce space, but then you spend more time. Now, if the data changes, if you add an additional bit, or if you add an additional node to a tree, can you reconstruct a succinct structure? That something is known, and there are more yet to be discovered. And here is a recent book on this, which actually has a whole lot of compact or succinct, well, it goes by compact data structure, succinct data structures. There are various words for it, and I think I will stop here. Thank you. I should say special thanks to Gokul for helping me with some of the figures. Okay.
Okay, so it's a good time to ask if there are any questions. Venkatesh, there's a question online. Can we not make the tree such that it is a chain/path of the whole word, and every node add a ending character $?
Can you read again?
Can we not make the suffix tree such that it is a path, just a path of the whole word, in a path of the whole word, and in every node add an ending character $?
The whole path, and every node you have a dollar thing.
Different $ symbols.
No, that doesn't really help in searching, because the key for suffix trees is this observation. Okay. Yeah, this observation that your pattern occurs in the text if and only if it's a prefix of some suffix. And that's what enables you to build all the suffixes. That path with $ doesn't actually add all the suffixes.
Okay.
No.
So,
yeah.
So two questions. One is, so the representation of a tree as a sequence of parentheses. Apart from the space thing, so a tree stored traditionally will be all over the CPU memory, and so you will have cache misses all over the place. And this parenthesis row is basically an array, and it seems to me you will get a huge speed up by keeping things in the cache, avoiding cache misses. Is that possible?
There is a lot more actually. Maybe I didn't say it. First of all, the big difference is in the space. Okay, the tree has pointers all over. Yeah, all over memory is one problem. Here it's a nice little array. And I said it but didn't emphasize much that in this tree pointer representation, left child, right child, parent, even parent you need to have another pointer. But in this representation, not only it reduced space, people found out that the functionalities are huge. In fact, there are papers where there is this whole page of operations one can support in constant time, number of nodes in this level, leftmost leaf, rightmost leaf. These are some of the things which in the classical representation not easy to represent unless you have some additional pointers. So this is not only reduce the space, it increase the functionality better. Okay, there's one more thing. Another thing is, usually in a tree you actually store some values on the nodes. Right? A tree is just not about just pointers, and every node you have some values stored. So again, I didn't emphasize much that this mapping between the nodes of the tree and the parenthesis sequence tells you that you can store whatever you want to store in a separate array and still get that information without any problem.
Yeah, so in that context, actually, a similar parenthetic sequence is used. It's called the Nevic tree format. It's used in phylogenetics to represent a tree as a string. But I don't know whether people actually use it directly to query and so on, or it is just a printable representation of a tree.
Yeah, to answer queries, you need a lot more additional information, which is that little o, I quickly pushed it aside. There you need store a lot of information. Okay, so and parenthesis sequence is not the only representation. As I said, quickly people came up with different kinds of 0-1 sequences by traversing the tree in different ways and still support different kinds of functionalities.
So this little o thing reminded me of what happens in the FM index, where you index a subset of the queries, and then you have to, if you get something else, you have to do some calculation to get it.
Yes, so little o is basically, you store some information for parse. So on this n-bit string, suppose I store the answer for every log square n position. Okay, then the total space is n by log square n into whatever I store. That will be a log n bit answer. So that's overall n by log n. So it's little o of n. Okay, so this is the game. Usually you store some partial information which brings it under little o, but whenever the information is not stored, you have to do some hard work to answer the query. You have to go up and down wherever some answer is stored and get them.
There are any further questions from participants, audience? Okay, there doesn't seem to be any question. Let's thank the speaker once more.
Okay, thank you.